Okay, folks, welcome to Lecture 6, and in this lecture we'll be taking a look at the second quadratic functions lecture, analyzing them. So, just to see where we are, we've looked at linear functions, we're now on quadratic, these are the other functions we'll cover, and then we'll just do a bit of delving deeper into functions with the last two topics. So, just some of the things you should know. Quadratic function, highest power on the input is 2. There's the simplest equation, the general equation, typical graph, either for positive a or negative a, smiley, not smiley. And then some examples we'll go through. We've gone through some of these. Area, be it the area of diameter of a pizza, of a pipe, of an artery. We looked at stopping distance of a vehicle, we looked at kinetic energy, wave power. So these are all practical examples of quadratic functions in the real world or in science. So here's a problem. We're looking at a micro turbine producer and increases the blade length from 2 meters to 2.5 meters. So the area is governed by a quadratic relationship with R. Calculate the percentage increase. So what we're really looking for is the new area over the old area. So it's going to be pi. Now the blade length is the radius. So new over old, so it's 2.5. Sorry, actually. Squared over the old, which is 2.0 to be squared. Now we don't actually need to get our calculators because we can cancel pi there. This is really now 2.5. Remember, the squared can go like this. And this will be 2.5, so 5 over 4 to be squared, which is 25 over 16. Now I'm just staying without the calculator. Sorry, that's to be squared. When we work this out, we'll get 156, but they'll cancel out. Just be careful then, guys. What's the percentage increase? So the original turbine was 100% plus. So the percentage increase is 56.25. So just be very careful with that. So percentage increase 56.3 when we go to 3 significant figures. Wastewater treatment pipe, WWTP. Sorry, wastewater treatment plant, not pipe, is been upgraded. The diameter of the inlet pipe is been increased from 60 to 90 centimeters and determine the percentage increase in flow. So again, we're looking for the new area over the old area. Going into radiuses. You could actually keep the diameters in there because the ratio is still the same. So if you wanted, you could actually stick the old diameter and the new diameter, but I'm sticking with the formula, putting radiuses in. Again, guys, the pi will cancel out. If I divide top and bottom, that'll be 3 over 2 to be squared by 100, which is 9 over 4 by 100. So it'll be 9 by 25. which gives me 225%. Now again, remember that's not the percentage increase, that's the new amount of flow compared to the old flow. So the increase so that's our increase. So, question for you guys to try. 6-inch pizza contains 600 calories. How many calories are there in a 10-inch pizza? So simply new area over old area and multiply that by the calories, and that will give you, so we're just looking for the number of calories. There's no percentage increase in this question. Another one, similar, exact same maths, just different scenario. 7-inch pie contains 6 adult size portions. And assuming the portion size is the same, how many would there be in a 10-inch pie? So again, you can just use that formula there. But very quickly, guys, you're really just looking at the ratio of new over old to b squared. And if you actually just stick those values in, you'll get the correct answers out. The main thing, guys, is area is a quadratic relationship. Double the input quadruples my output. Looking at an artery now, so I'll work this problem out. An artery has lost 12% of its diameter. Determine the percentage reduction in blood flow. So just again, be careful of what the question is looking for. So the new artery, guys, the area, constricted area is going to be 88% over the old original artery, which was obviously 100%. When we work this out, the new artery has only 77.44% of the original, which was 100. So this isn't the answer, guys. We're looking for the percentage reduction. So in this case, there was a 22.6% reduction in flow. Problem for you guys to try. Artery has lost 60% of its diameter. So calculate the percentage reduction in blood flow. So exact same as I did. Just be careful as you're working things out. We're looking for the percentage reduction. It's just an example showing how an artery with 1/3 obstruction results in a 50% loss of area. Half of the artery is blocked. That means 75% is lost. And if 2/3 blocked, so this is a deep blockage, in that case 90% of the cross-sectional area is lost. So again, it's just important, like this quadratic relationship is kind of in lots of different places where you probably didn't think about before. Now we're going to look more at the maths of stuff, kind of the analysis part. So when we're asked to solve a quadratic equation, for example this one here, what we're really asking is what values of x. If I feed a particular value of x in there, I want to get an output equal to 0. So what value of x will give me an output of 0? When we draw it on a graph, I'm looking for these values here, because remember that horizontal line is my output is 0. So I'm saying what x values will give me an output of 0. We call this the roots. What are the roots of the curve? Where the curve of the function cuts the x-axis. So here we can see the roots. One root is x is equal to 2, and the other root x is equal to 3. So that's when we solve, that's what we're finding. Last semester we used factorization. We're going to take a quick blow over that again on the next slide, very quick. But this semester we're going to, because we don't, in science we tend not to come across the nice equations that maths books often throw out. So this is just from our slides from last year. So if we're given this one, if this equation here, this is a trinomial, then this equation here, we solve it using the difference of two squares. And this is the simple factorizing one. 3x is common to both terms. So we'll take a look. This, we'd factor this one. We'd let each factor equal to 0. So this now is the equation solved. And if we were to draw a graph of it, it's a smiley curve. Cuts here at +8. And there's the typical curve. Difference of two squares. So now the left-hand bracket, let that equal to 0. We get x is equal to 2. That should be equal to +2. Yeah, I've just written them in the wrong order. But they're still the same roots. When we draw our curve, it looks like this. Here, 3x is common to both terms. Take that out. Let each bracket equal to 0. And there's our typical curve. The problem, like I was saying, guys, is in the real world of science, we just don't get nice whole numbers in here. It's much more likely going to be 0.418 x squared minus 3.72x plus 1.8953 ... That's much more typical of the kind of quadratic you'd come across in science. So these methods just don't really apply. They apply nicely in the nice safe world of maths, but as soon as you try and bring it into the real world, these methods just, you'd never really in a laboratory situation have even an opportunity to use them, or very rarely. So for this reason, guys, we use what's called the quadratic formula. Now, a lot of people use this as a safety net, and for some people it's kind of a go-to, go straight to this problem. It's most people get it wrong. I get it wrong. I never trust it myself, and I've been using it for, I don't know, 40 years. So be really careful with it, guys. There's so many pitfalls. It's just laden down with the opportunity to screw things up. So approach with caution. The most important thing, guys, is to get your labeling right. Remember what I said at the beginning of lecture 5. A belongs to the quadratic term. B belongs to the x term, and C is the constant. It doesn't matter what order things are written in, guys. It's not the first thing is A, the second thing is B, and the third thing is C. You've got to watch out for that, and I will always try and trip you up with it, so just be careful. So your first step is to write out A, B, and C independently. Don't just pull them from the equation as you go. Trust me on this. So with all that said, guys, you guys have a go at this one. So just pause the video here, give this a go, and see what answers you get. So I'm going to push on now. But please do give it a go. And now in the next slides, what I'll talk is about a deeper analysis of using the formula and stuff. But I'd like you to kind of give it a go first and just see, okay, where do I feel a bit weak? So pushing on, guys, we're going to now take a look at the engine of the quadratic formula. Most people just get out their calculator and start tapping away. What I'd suggest is approach things a little bit more clinically and take a look at the heart of the function, and that's this bit here. The bit under the square root sign determines everything, and often determines whether you can just actually walk away from the problem and go, no, there's nothing to be seen here, there's no answer to the question. So this bit, guys, is called the discriminant. And it allows us to determine the number of roots. So if this value here, guys, when you work this out, if that value is greater than 0, then you're going to have 2 roots. The graph will look something like this. Now, alternatively, just to be clear, it could also look like that. But either way, it's going to cut the x-axis in 2 places. If the discriminant is equal to 0, then, guys, there's only 1 root. And what that means is your curve looks something like this. It only touches in 1 place. Or again, alternatively, it might look like that. Imagine it's touching there in the 1 place. But there's also a possibility, guys, if this bit is negative, if it's less than 0, then there are no roots. And you haven't done anything wrong. It's just the curve, guys, looks like this. It doesn't actually cut the x-axis at all. So, and lots of quadratic functions don't have roots. You know, it's perfectly normal. But the discriminant is what will allow you to determine that. Now, you're not giving yourself extra work either, guys, because whatever way you're going to have to go about it, you're still going to have to work it out. It's still part of the calculation. But what I would always suggest is take that bit out, work that out, and then you can decide, well, am I looking for 2 answers? Am I looking for 1 answer? Or is there no answers and I can just walk away? So we'll take a look. So this is a past exam question, and it asks you to determine the roots of the function, both functions, and then to draw a rough sketch. So there's quite a lot of work in this question in hindsight. It's changed now a bit, but it's a good example of what I'm kind of looking for in an exam situation. So you could use factorization if you want. I'm not fussy. Most people will go for the quadratic, especially when I tempt them with it, but be really careful. So we take a wee look, guys. First thing, here's the first function, y. Now I'm thinking minus x squared. It's going to be not smiley. Next, guys, just again to be kind of clear, when x is 0, my graph is going to cut. When I let x equal to 0, y is 6. I also, as I said, I know it's not smiley, so it's probably going to look something more like that. So it's just always, just by looking at a curve, you can actually begin to tell a lot about it. Now be very careful, guys. There's my c. Minus 1 is my a value. And b, there's no x term, guys, so b is 0. So these are the 3 values I'm going to feed into the quadratic function. First of all, though, I'm going to take a look at the discriminant. So the discriminant, guys, adds up. Be very careful with your minuses. That's where you're going to make the mistake, guys. This minus here is your most likely point of error. So From the discriminant, guys, I know the discriminant is 24. So now I know I'm looking for two roots. So now when I go to the calculation, guys, I don't have to do this again. I know that value there is 24. Feed my values for B and A in. And now from this, guys, two answers fall out. I assume it's a positive, and I work that out. And then I put a minus in between them, and I work that out. That's what gives me two separate answers. So looking at the positives first. Minus 0, well, that's just 0, plus the square root of 24 over minus 2. It's a negative value. Positive over minus gives me a negative. Or else I put a minus in front of the minus 24, and that gives me my other root. Now when I go to draw the curve, I know my 2 points there. So this is just what I was saying earlier, is I now know it'll also cut here, and it'll cut somewhere here, and it'll cut somewhere there. Sorry, there. Oh, it's a bit out, yeah, just bad judgment. So that's what my curve looks like when I'm asked to sketch it. Taking a look at part 2. A is 2, B is minus 4, C is 9. Feed those in to the discriminant. So now my discriminant is negative. So essentially, guys, I can just stop there. There is no roots. Alls I know, the curve is smiley, because that value is positive, and that it cuts the y-axis at plus 9. So that's about all I can tell from the equation. And there's what the graph looks like, the real graph. So now, you guys use the quadratic formula to determine the roots of this function. And then sketch a curve of it, but I can't, when we're in the online format, I can't take a look at your sketch. So be aware of the pitfalls I mentioned earlier, guys. Just take it, take it step by step. I'll push on. So now we're looking at kind of more practical examples, the good old ballistic example of a thrown ball. This has been used by teachers of quadratic functions since day dot. So here, guys, we're told its height h with respect to time t is given by this function here, and t is in seconds. I should have had that information in the question as well. So first, sketch a curve of the function. We'll put that on the next slide. Determine the height of the ball at 0.5 seconds. So we'll read that off the graph. Determine the speed and direction of the ball after 0.5 seconds. So to find the speed, guys, we need to draw a tangent and then work out the slope of the tangent. Determine the maximum height reached by the ball, and when did the ball hit the ground. So we'll take a look. First thing, we draw the graph, so that was part A. What's the height at 0.5 seconds? So here's 0.5. We go up to the graph, and then we can read it off the graph. So now from the graph, guys, here in red is what you can kind of read off of the graph fairly accurately. But I hope you kind of agree that depending on how well the graph is drawn, hand-drawn graphs are just not that accurate. So if we actually fed 0.5 into the function, That's what gives us this much more accurate answer I've done it in grey. So what I have in red is what you can read off a graph. What I've added in grey is what you can, the extra detail you can get by proper analysis. Here we take the slope, so we draw a tangent at the point of interest. We pick 2 points. So there's my point, there's just the maths going on. Again, I'm just sticking with the 1.4. So sorry, slope formula. These are my 2 points of interest. And now, with a bit of rough maths, I can kind of work out that the slope there, that's the speed, 0.86 meters per second. Because it's a positive value, the slope is uphill. So that means, guys, at this point the ball is still traveling upwards, and we can see from the curve that that's exactly what's happening. On this side of the curve, any tangents will be negative, which means the ball is traveling downwards. So the slope not only gives you how quickly the ball is moving, it also gives you its direction. Is it increasing? Is my height increasing, or is my height decreasing with time? What's the maximum height? Again, I can draw a horizontal line across the top. And to there, guys, that's what I can kind of accurately, 1.82 meters. But like I said, with some proper maths, we can get an awful lot more detail. We'd have to use calculus in that case, finding the maximum height. Finally then, how far did the ball travel? We can see this is what we're looking for down here. Where was h equal to 0? So we'd use the minus b formula with this. The formula we were just looking at. From that, guys, you're going to get t, you're going to get a positive value, which is 3.18. And again, all those decimal places come from using the formula correctly. But you're also going to get a negative value. And what that would suggest, guys, it's probably going to be t is minus 0.43 or something like that. What the negative value would suggest is that if we went back in time, that if the ball was actually following this arc independent of the person throwing it, 0.43 seconds before the ball was here, the ball would have been on the ground. So that's all the second value, but in this case, that value is invalid. It doesn't make sense in the context of the problem. So what I'm really trying to say here, guys, is kind of, first of all, drawing a graph is quite cumbersome, especially trying to do it accurately. Secondly, then, any analysis we do using the graph, firstly, it depends on the quality of the graph you've drawn, and secondly, it's kind of this eye judgment thing. Is that 1.42 or is that 1.43, or is it halfway between them? That kind of judgment is very hard. Whereas with proper analytical maths, we can arrive at exact values. And as scientists, that's what we want. So that a scientist could do the problem in Russia, or he could do the problem in Ireland, and both scientists would absolutely agree on the outcomes. So that's what science is all about. So now, here's 2 problems, guys, question 6.6 and 6.7, but the graphs are on Moodle, so I don't expect you to draw the graph. I've already got the graphs up on Moodle. What I want you to do is just do that bit of analysis. So the graph is given to you on Moodle, like I said. What's the height of a bungee jumper? So this is a bungee jumper, guys. It's going to be a smiley curve with no roots, because otherwise bungee jumping wouldn't be very popular. If you slapped the ground and then got dragged through the earth and pulled out the other side, it wouldn't quite appeal for your backpacking trip. Use the graph to determine the maximum distance the bungee jumper fell. and draw a tangent to determine the speed of the jumper after 4 seconds. So you guys will have to go to Moodle, get the graph, and then give those a go. Similar, here's the graph actually. So what's the height from there? Read it off the graph. What's the maximum distance she fell? So you'll have to subtract that from here, guys. That's what we're looking for. What's the distance she fell, not her height above the ground? Get the slope, so draw a line, tangent at the point of interest, pick 2 points, get the slope. In this case, guys, it's a negative slope, so the bungee jumper is still traveling downwards. And then it's really a case of what are the values for the rise and run. And that's really what I'm trying to teach, guys, is that everyone is going to have this red line at slightly different angles. So intuitively, you kind of know at the back of your mind that it's not the most accurate way of arriving at this answer. There has to be a better way. There is. We'll meet that at the end of the course when we're looking at calculus. Here's a similar problem, guys. It's a bit of a messier looking function. Don't be put off by it. It's still a quadratic. This is just a number. So it's still just a simple quadratic. It's not smiley because the minus in front of the x squared. Draw a graph of the function. That's drawn. All the measurements are in feet in this case. And note as well, guys, it's actually height of the ball over distance traveled. So both of these axes are marked off in feet, which just might look a little bit weird, but that's just the way the question is worded. And I'd kind of like to try and keep everything shifting, that you're not, that you get used to seeing lots of different things. So determine the height of the ball, how far was the golf ball hit, and estimate the rate. Rate, guys, means slope. So the golf ball graph, as I said, is on Moodle. Here's just a quick look at it. You're asked what was the height at 250 feet. So you want to work out that height there. What was the height at 400 feet? Again, bring it back to there. What was the distance the ball travelled? Well, what's the distance there? You could work it out using the quadratic formula, and at least then you're right. That will definitely get you the right answer. One answer will be 0, and one answer will be this. And then finally, what was the speed of the ball? We can tell the ball is still heading upwards. Or no, not the speed. What was the rate of climb of the ball? So for every foot it travels, what's the height gain? And again, guys, you'll see that rate of climb is changing at every millisecond of the ball's flight. That slope is constantly changing. Here it's horizontal, then it starts to go down. So analyzing these kind of functions using tangents just becomes very unwieldy very quickly. But again, you guys have to arrive at some kind of answers to these questions because they will be asked in the tests. So make sure you give them a go. As well, guys, just you'll notice there's a good few questions of this lecture, but there was no real questions in the last lecture, and it's just the way the course will kind of unravel. Sometimes you'll feel you have lots of questions associated with the lecture, and then 1 or 2 lectures might go by when there's no questions asked. So that's just the nature of the module delivery. Finally then, guys, just a quick wrap up. We'll just take a look at where parabolas occur in real life. So Angry Birds is perfect example. All of these trajectories you decide by moving your finger around, they're all parabolic. Any missile launch, ballistics, is all based on parabolas, especially the older style missiles, the intercontinental ballistic missiles and stuff. you had to dial in your A, B, and C in order to make sure that your missile had hit wherever you so decided. Same with a tennis ball, exact same philosophy going on. Car reflector, so any kind of reflector in your car headlight, that shape is parabolic. Same for a solar collector if you're using solar thermal tubes on your roof to gather the sunlight. All satellite receivers, big and small, parabolic. Any water jet, so even if you just get your hose and spray it up in the air, and as you move your wrist, you would be changing the parameters of A, B, and C as far as the water jet is concerned. They would always be as well minus x squared functions because of their shape, the not smiley shape. Sand dunes as well, if the wind is blowing, say on shore for a long period of time, these parabolic dunes are very often created. Architecture in loads of different guises, all based on parabolas. And even the path of a comet is also traced by a parabolic curve. So we'll finish up there, guys. So thanks for listening, and we shall meet again for the next video, which is on cubic functions.